In this video, we'll talk about the last case that we could not solve before for integrals of powers of sines and cosines. And this is going to require a new technique called reduction formulas to solve out completely. So, like we mentioned in the last video, there are some choices of m and n where we cannot yet handle this integral, integral of sine to the m of x, cosine to the n of x, and these are ones where m and n are both even. So here's an example of one such integral. Evaluate the integral of sine to the sixth x times cosine to the fourth x dx. So our substitution trick here is not going to work, right? We don't have an odd number of either sines or cosines to sort of pull one out for a du term, convert the rest into the other function, and then make a substitution to make this happen. It's just not going to work for the way we have this problem set up. So what can we do instead? Well, let's just start by applying some Pythagorean identities and see where that gets us. We could try, and it's probably the way you want to go on this problem, to get everything in terms of just sine functions, right? U sub's not going to help us, so there's no point in having a mix of sines and cosines. Let's get to all sine functions, see if that gives us any ideas of how to proceed from here. So I want to convert that cosine to the fourth term into just sine functions, so I can rewrite this as the integral of sine to the sixth x times 1 minus sine squared of x squared dx. I can expand this out and then distribute terms through. And now we're sort of sitting here stuck and not much to do, right? We can't integrate these functions. We don't have the cosine x to do a u substitution, and we're kind of sitting here not really knowing what to do. But what we notice here is that all these powers are even. So we're sitting here with a bunch of even powers of sine, and now where else really to go with it? So let's take a step back and see if we can figure out the simplest case of that situation. And what's the simplest case? Well, the simplest case is taking sine squared of x as the smallest even power. So what can you do on this problem here? Well, this is where we have our half angle formulas coming back to help us, right? Based on our half angle formula, which says that sine of x over 2 is square root of 1 minus cosine x over 2, I then know that I can write sine squared of x as 1 minus cosine of 2x all over 2. And that gives us a way to integrate this function. So the integral of sine squared of x dx is equal to the integral of 1 minus cosine of 2x over 2 dx. I can then split this up into two parts and then integrate each term. The second one, if you want, is a substitution for 2x, or you can just do it directly. And that's what I get for my answer. So using our half angle formulas, we can handle the smallest case. We can handle the power of 2k's, and that's sort of a good start as how we're going to solve this problem. Now the question becomes, how can I get from those 6th power, 8th power, 10th power things I had before down to the second power that I know I can solve? And that's where these things called reduction formulas come into play. And here's an example of a reduction formula. The next video in this set will talk about how you figure out and derive these formulas, but in this case we're just going to use this formula here to solve this problem. So here's our formula we need here, and if you see, it converts an integral of sine to the nx into an integral of sine to the n minus 2x. If you look at this, you'll see it's probably integration by parts, which it is, and we'll see that in the next video. But the point is, this will convert the integral of sine to the 10th into sine to the 8th, then 8th into 6th, 6th into 4, 4 into squared, and then we know how to solve the squared problem. And so these problems can get long and tedious, but as long as you work through things slowly and gradually, you'll get to the right answer at the end of them. Let's go back to the integral we had before. This is going to be a long one, but we'll get through it. So I have integral of sine to the 6th times cosine to the 4th of x dx, and we'd done work before to reduce this to integral sine to the 6th minus twice sine to the 8th plus sine to the 10th. Now in order for this to work out better in my head as we solve this, I'm going to flip these terms around and put the sine 10th first, because the way you want to handle these is start from the highest power and work your way down. It'll give you less overall steps than if you sort of do it all at once or do it in a different order. And you'll see why as we start going through this. And so I split up my integrals into this form here. Now I want to apply this reduction formula up here to the sine of the 10th term. So I'm applying it at n equals 10. So applying at n equals 10 tells me that this integral here I can rewrite as negative 1 over 10 sine to the 9th of x cosine of x plus n minus 1 is 9 over 10 integral of sine to the 8th of x dx. And now I'm going to write my other two terms in here, just carry them down. Okay, now I want to combine some things. And we'll notice I have two terms that both have integral sine to the 8th. I can put those together into a single integral. And this is why you want to start from the highest power, because you'll be able to combine it at every step as opposed to doing this multiple times over. So we'll carry down the first term. We'll combine the second two, which becomes a minus 11 over 10 integral of sine to the 8th of x dx. And we still have our sine to the 6th hanging out over here. That will come into play at the next step. Now I want to apply reduction on this next formula, on the sine to the 8th term, which I'm applying the formula, this one up here, with n equals 8. If I do that, I will get the following terms, like this. So negative 1 over n is negative 1 over 8, sine to the 7th cosine x, plus the n minus 1, which is 7 over 8, sine to the 6th x dx. I'm now going to distribute coefficients and then combine terms like before. So there's my distribution. And we see that if I put the two integral of sine to the 6th terms together, I will get just a plus 3 over 80 integral sine to the 6x dx. Now I want to apply the reduction formula on the sine to the 6th term, and you'll see where this problem's going, right? I'm going to apply it on 6, get a formula for there. Apply it on 4, get a formula there. Apply it on 2. Well, on 2, then I'm done. I know what the answer is at that point. I can just use the sine squared integral to get my answer. So let's apply it on here with n equals 6. And now there's no combining. We can just distribute terms like before. I can then apply the reduction formula for n equals 4, distribute terms, and then finally apply the formula that I know for the integral of sine squared, or the substitution formula, and integrate to get to my final answer here. And then that right there is your final answer to the problem. So these problems can be long and tedious, and depending on how high of power you have there of sine or cosine, but the idea is always the same. The idea is always, let's take these high even powers and then step one at a time, down, lower, and lower, getting one more term at each step until I get to an integral that I know how to solve, namely that of sine squared of x. So if you take your time with these problems, you'll see how they all come together, how they all work, and how you can work these problems out using the reduction formulas. We don't yet know how to get those yet. We'll get them in the next video, but knowing how to use them to solve problems is a very important part of this process for solving trigonometric integrals.